Good to have you back, everybody. Let's think about an atomic symbol for magnesium. Let's say I have magnesium 24. We know from previous experience that the 24 represents the total number of protons and neutrons in this particular isotope, and that number, which we call the mass number, is always going to be a whole number. But it turns out if you take a hard look at your periodic table, you're going to often find below the element itself, you're going to find a number that is rarely a whole number. Why did that happen? Where does that come from? And I think this is our first clue that number, 24.305, even though it's very similar to the 24 we found for the mass number, represents something a little bit different. It's almost never a whole number, and there's a reason for that. Let's take a look. If you go to the next slide, what you're going to see is a sample of magnesium metal that we're trying to zoom in on and take a look at some of the atoms within that particular sample. And what you're going to notice is that there are actually three different isotopes present for magnesium. We have magnesium 24, which we discussed before, but we also have magnesium 25 and we have magnesium 26. We know that the number of protons doesn't change, so that means the number of neutrons in each of these isotopes must be a little bit different. Let's take a look at something really important. Let's count all of the magnesium 24s. Here's one, here's another, two, three, four, five, six, seven, eight, 9, 10, 11, 12, 13, 14, 15, 16. So it turns out in that sample, which I counted earlier, has 20 atoms, 16 of the 20 atoms are magnesium 24. If I go to count the other ones instead, let's say that we look at magnesium 25. I've got one, two atoms that are magnesium 25. So let's write that one down as well. 2 out of 20 are magnesium 25. And then let's take a look at our third isotope, which in this case is magnesium 26. Again, I've got two isotopes that are magnesium 26. So we'll go back to our pen and write that down as well. 2 out of 20. Now, if you actually do the math on these fractions, that means about 10% of our atoms are magnesium 26, about 10% are magnesium 25, and about 80% are magnesium 24. So the vast majority of the atoms in this sample are magnesium 24 isotopes, but there are a handful of magnesium 25 and 26 atoms as well. These percentages that we just wrote down, they represent what we call the natural abundance of this particular sample. And if you looked at millions and trillions of atoms of magnesium, what you would find is that percentages stay pretty much the same. If I look at magnesium 24, it's almost 80%. If I look at magnesium 25, it's about 10%. And magnesium 26 is about 11%. This is looking at a sample not of 20 atoms, but of millions or billions or trillions. Here's another thing that's interesting. It turns out when you put 12 protons and 12 neutrons together, the mass of those 12 protons and neutrons is actually a little bit less than you expect it to be. It's 23.9850, what we call atomic mass units, slightly less than expected. We expect 24 protons and neutrons to have a relative mass of 24. They're a little bit less. The same thing happens with the magnesium 25 and 26. Their masses are a little bit less. We're not going to go into too great a detail on this, but what we would say is that essentially some of the mass of those protons and neutrons is being used as energy to hold the nucleus together by something we call the strong nuclear force. And so we lose a little bit of mass when we put all of those protons and neutrons together. We're a little bit sidetracked though. I want to know, if I go back, I want to know, where did this number 24.305, where does that come from? Well, it's an average, but it's a special kind of average. When you're in math class and you're asked to find an average, you say A plus B plus C, and you divide it by the total number of values, in this case 3, to get an average. You know what that does? That treats A, B, and C like they're equals. And in the case of finding what we call average atomic mass, we don't have equal isotopes. Magnesium 24 is much more prevalent than either 25 or 26. So instead of a standard average, we're going to calculate what's called a weighted average. And this is how you do that. You take each isotope's mass, so 23.9850, and you multiply that by its percentage, 78.99. Then you add to that the second isotope, 24.9858, and you multiply it by its percentage. And you add in the third isotope, 25.9826, multiplied by its percentage. And instead of dividing by 3, what we need to divide by is by 100. That gets us away from those percentages. So when I do this calculation on my calculator, what I end up with, and I'm going to round here, is 24.31 AMU, atomic mass units. Those AMUs are very, very close to the 24.305 that we saw underneath the atomic symbol. So if I look at a periodic table, I can find the average atomic mass to check my answer to make sure I've done it right. And as long as it's close, you know you've done a good job. I want you at home to try the same thing using this separate problem with oxygen. You're going to do it exactly the same way, and you're going to check your answer against the periodic table to make sure that you've done it correctly. In fact, I'll go ahead and tell you, you should have an answer close to 15.999 AMU. Pause right now, pause the video, and do this problem to make sure that you understand what's going on. We're going to skip ahead, though, to the next problem, which is a problem I really love. It says boron has 2 naturally occurring isotopes on Earth, boron 10 and boron 11. The question they ask at first is, which of these 2 isotopes is most abundant? But they don't give us any of the percentages that we were given in the previous problem. So how do we know what is boron's uh, what is boron's average atomic mass? That's probably the best place to start. If I look on a periodic table, it's usually listed as 10.811 AMU. Well, this is all I need to know to figure out which one of the two isotopes is most prevalent. This number is between 10 and 11, right? But it's closer to 11, which means I must have more boron 11 than I do boron 10. Let's prove it. We're going to do that by solving for those natural abundances. Here's how you would do that. Take from your periodic table the average atomic mass, so 10.811. And again, I got that from the periodic table. We're going to set that equal to boron 10, which is 10.0129, times X. We don't know that percentage, so we're solving for it. Then we're going to add to it boron 11, which is 11.0093, times not Y, but if both of these have to add up to 100%, we can say that boron 11 is 100 minus X. And we still divide by 100. Now I'm going to cross multiply first. And when I cross multiply, here's what I get. 1081.1 equals 10.0129x plus, and I need to distribute, 1100.93 minus 11.0093x. Now, the first thing I'm going to do is get the like terms together. So I'm going to subtract 1100.93 from both sides. Let me get out my calculator and see what that comes out to. So on my calculator, 1081.1 minus 1100.93. And I get negative 19.83 equals, and I'm going to put my X terms together, 10.0129 minus 11.0093. And I get negative 0.9964x. Now all I have to do is divide both sides by negative 0.9964. And that will give me X. So I do that on my calculator. Negative 19.83 divided by negative 0.9964, and I get 19.9. That's a percentage, and that's equal to X. Well, what's X? X is the percent of boron 10. We would say 19.9% is its natural abundance. If I wanted to find boron 11, I need to look at this part. It's 100 minus X. So if I say 100 minus 19.9, I get 80.1%. So by far the most prevalent isotope of boron is boron 11. Okay, let's do some practice on our homework sheet. See you soon.